So I'm acknowledging the fact that I'm doing a video recording, and now let's move on. So I do want to convey yet again sort of the overall picture. What we're going after is a new relationship between computation and sciences. Specifically, if we look throughout the history of science and mathematics, computation has sort of been the slave. It's been for the first several hundred years, computation was what you did in order to test or verify or in some way exercise the mathematical side of scientific theory, mathematical theory. Computation wasn't interesting of its own right, in its own right, especially in the sciences. In mathematics, that was, we can equivocate about that. But in science, computation was definitely in the sort of slave role to the sciences. And what I want to do is to get across this idea that in the next 100 years, the roles are going to reverse, in the sense that we're going to see the next 100 years as really being about what computation says back to mathematics and the sciences, the physical sciences. We're already seeing this start to happen. There are these harbingers, sort of bleeding edge folks, like John Wheeler, the physicist, who has talked a lot about it from bit. In fact, there's a whole crowd of folks who are thinking about how the physical world arises out of computational dynamics, and that's what we're, in some sense, that's what we're going after. But we're going after it in a larger context, because the question is, how do I say this? There are many different reasons or motivations for trying to think about the physical world or physical dynamics as arising from computation. But my motivations are practical. I argue that there are certain kinds of computational frameworks that actually make certain classes of calculations feasible, and that those calculations have been infeasible up to this point, and that the physical sciences are at a point now where they're addressing systems of such scale and complexity that this is a serious issue. We're seeing this all over the map. Chemistry, biology. We're up against systems of enormous scale. Probably the paradigmatic problem of scale is the issue of marrying quantum mechanics with general relativity. In some sense, and in some very real sense, this is about marrying conceptions of the very small with conceptions of the very large. And at present, we don't have good theories, good workable theories that marry these two ideas and enable us to make physical predictions. And yet, when we talk about practical systems, we are very much interested in systems where the dynamics of these physical systems span scales. A really good example is dynamics in signaling networks in the cell. We can have this cartoon picture of the cell as kind of two nested circles. The outer circle is the perimeter between the cell and its environment, and the inner circle is the division between the cytoplasm and the nucleus. And when environmental stimulus impinges on the outer circle, signaling processes are set up inside the cytoplasm that are taking place in the subsecond region. Whereas ultimately those signaling patterns when they go into the nucleus. They're affecting genetic regulatory. I mean, they're really affecting the production of proteins via the genetic material, and that takes place on the order of hours, certainly minutes. Um, so you're talking um, differences, several orders of magnitude in terms of differences of temporal scale. We can also find examples of differences in spatial scale as well. But rather than delve into a lot of these examples, all I'm trying to get across is that in order to reason effectively now about the dynamics of physical systems, we are up against issues of scale.